Welcome to our asynchronous session, the lesson for atmospheric humidity. For an overview, the module examines the concept of atmospheric humidity. It begins by looking at the hydrologic cycle and the circulation of water in our atmosphere. It then looks at the different phases of water, showing how evaporation, condensation, and saturation occurs at the molecular level. And here we learn that there are many ways of describing humidity. So the learning objectives of the module is for the students to be able to describe and outline the process of circulation of water in the atmosphere, create a table comparing the phases of water, and lastly, define, compare, and contrast absolute humidity, specific humidity, vapor pressure, and relative humidity. Before you answer, of course, your module, you can use what I know column to list the things that you know about the topic, atmospheric humidity, and then list the questions you have in what I want to find out column. Again, note that there are no wrong answers in these two columns. And after finishing reading the module and watching this video, use what I learned column to list the things you learned, and you use bullet for your answers. To commence, we know in our previous modules that in our atmosphere, the concentration of the invisible gas water vapor is normally less than a few percent of all the atmospheric molecules. Yet, water vapor is exceedingly important for it transforms into cloud particles, and these particles that grow in size and fall to Earth as precipitation. In tropical countries, we experience rain, and that is a form of precipitation. The term humidity or atmospheric humidity can describe the amount of water vapor in the air. To most of us, a moist day suggests high humidity. So that we may better understand the concept of humidity, we will begin this discussion by examining the circulation of water in the atmosphere. Then, we will look at different ways to express humidity. Over the ocean, the sun's energy transforms enormous quantities of liquid water into water vapor in a process called an evaporation. The winds that transport the moist air to other regions where the sea water vapor changes back into a liquid or ice, forming clouds, is a process called as condensation. Under certain conditions, the liquid cloud particles or the solid ice crystals may grow in size and fall to the surface as precipitation. Precipitation may be in form of rain, snow, or hail. If the precipitation falls into an ocean, the water begins its moving or its cycle again. If, on the other hand, the precipitation falls on a continent, a great deal of water returns to the ocean only after a complex journey. This cycle of moving and transforming water molecules from liquid vapor and back to a liquid again is called a hydrologic cycle or water cycle. In the form with which we are most concerned, water molecules travel from ocean to atmosphere, and to land and then go back to the ocean. So in form of runoff and groundwater and then percolation in the ground, and it will be released in lakes and then going to the ocean again through rivers and streams. So this figure here illustrates the process of hydrologic cycle or water cycle. Before falling rain ever reaches the ground, a portion of it evaporates back into the air. Some of the precipitation may be intercepted by vegetation, or it evaporates or drips to the ground long after a storm has ended. Once on the surface, a portion of the water soaks into the ground by percolating downward through small openings in the soil and rock, forming, of course, groundwater that can be tapped by wells. Wells. What does not soak in the ground collects in puddles or standing water or runoffs into streams and rivers which find their way back to the ocean. Even the groundwater moves slowly and eventually surfaces, only to evaporate or be carried seaward by rivers. Overland, overland, a considerable amount of water vapor is added to the atmosphere through evaporation from the soil, lakes, and streams. Even plants give up moisture by a process called transpiration. And the water absorbed by a plant's root system moves upward through the stem and emerges from the plant through numerous small openings on the other side of the leaf known as the stomata. Now let's talk about the phases of water. In this figure, this is a water molecule. The bulk of the head of the molecule is the oxygen atom. The mouth is a region of excess negatively charged. The ears are partially exposed protons of the hydrogen atom, which are regions of excess positive charge. So here are the three states of matter: water as gas, as a liquid, as a solid. When we look at many water molecules, we see that as a gas, water vapor molecules move about quite freely, mixing well with neighboring atoms and molecules. The higher the temperature of the gas, the faster the molecules move. In the liquid state, the water molecules are closer together, constantly jostling and bumping into one another. If we lower the temperature of the liquid, water molecules will move slower and slower until, when cold enough, they arrange themselves into an orderly pattern with each molecule more or less locked into a rigid position and able to vibrate but not able to move about freely. In this, it will be a solid state called ice. The shape and charge of the water molecule helps arrange the molecules into six-sided hexagonal crystals. As we observe in the ice crystal in freezing air, we see an occasional molecule gain enough energy to break away from its neighbors and enter into air above. The molecule changes from an ice molecule directly into a vapor molecule without passing through the liquid state. This ice to vapor phase change is called sublimation. I know that you have background already with these terms. So if a water vapor molecule should attach itself to the ice crystal, the vapor to ice phase change is called deposition. And if we apply warmth to the ice crystals, its molecule will vibrate faster. In fact, some of the molecules will actually vibrate out of their rigid crystal patterns into a disorderly condition. That is, the ice will melt. And so, water vapor is a gas that becomes visible to us only when millions of molecules join together to form tiny cloud droplets or ice crystals. In this process, known as a change of state or simply phase change, water only changes its disguise, not its identity. That means it disguises in different phases, but it does not actually lose its identity. It's still water. Now let's talk about evaporation, condensation, and saturation. Suppose we were able to observe individual water molecules in a beaker as illustrated in the slide. What we would see are water molecules jiggling, bouncing, and moving about. However, we would also see that the molecules are not all moving at the same speed. Some are moving much faster than others. At the surface, molecules with enough speed, that means traveling in the right direction, would occasionally break away from the liquid surface and enter into the air above. These molecules changing from the liquid state into the vapor state are said to be evaporating. While some water molecules are leaving the liquid, others are returning. Those returning are said to be condensing, as they are changing from vapor state to liquid state. When a cover is placed on the beaker, after a while, the total number of molecules escaping from liquid, or which we said earlier, evaporating, is balanced by the number returning, or what we said earlier, condensing. When this condition exists, the air is said to be saturated with water vapor. Under saturated conditions, for every molecule that evaporates, one must condense, and no net loss of liquid or vapor molecules results. If we remove the cover and blow across the top of the water, some of the vapor molecules already in the air above will be blown away, creating a difference between the actual number of vapor molecules and the total number required for saturation. This helps prevent saturation from occurring and allows for a greater amount of evaporation, just as if wind were blowing atop the surface, or I mean water surface. Wind therefore enhances evaporation. The higher or the faster the wind velocity, the higher the evaporation rate. For the plants, the faster the wind velocity, the higher the transpiration rate or the water loss from the plant. The temperature of water also influences evaporation. We all know that. All these being equal, water or warm water will evaporate more readily than cool water, right? Because when water molecules are heated, they will speed up. At higher temperatures, a greater fraction of molecules have sufficient speed to break through the surface tension of the water and zip off into the air above. In other words, the warmer the water, the greater the rate of evaporation. Again, the warmer the water, the greater the rate of evaporation. The higher the temperature, the faster the molecule moves. If we could examine the above air from in this figure here, we would observe the water vapor molecules freely darting about and bumping into each other, as well as into neighboring molecules of oxygen and nitrogen. When these gas molecules collide, they tend to bounce off one another, constantly changing in speed and direction. However, the speed lost by one molecule is gained by another, and so the average speed of all the molecules does not change. Consequently, of course, the temperature of the air does not change. Mixed in with all of the air molecules are microscopic bits of dust, smoke, salt, and other particles are called condensation nuclei. So called because water vapor condenses on them. Now, in the warm air above the water, fast-moving water vapor molecules strike the nuclei with much impact that they simply bounce away. However, if the air is chilled, if the air is chilled with cool air, the molecules move more slowly and are more apt to stick and condense to the nuclei. When many billions of these water vapor molecules condense into the nuclei, tiny liquid droplets will form. We can see then that condensation is more likely to happen as the air cools and the speed of the water vapor molecules decreases. That means it will slow down. As the air temperature increases, condensation is less likely because of the water vapor molecules have sufficient speed or sufficient energy to remain as a vapor. As well, we see in this and other succeeding chapters later on, condensation occurs primarily when the air is cooled. Even though condensation is more likely to occur when the air cools, it is important to note that no matter how cold the air becomes, there will always be a few water vapor molecules with sufficient speed or sufficient energy to remain as a vapor. It should be apparent then that with the same number of water vapor molecules in the air, saturation is more likely to occur in cool air than in warm air. This fact often leads to the statement that warm air can hold more water vapor molecules before becoming saturated that can cold air, or simply warm air has a greater capacity for water vapor than does cold air. At this point, it is important for us to realize that although these statements are correct, the use of such words are whole as hold and capacity are misleading when describing water vapor content, as air does not really hold water vapor in the sense of making room for it. That means the water vapor does not really hold, but giving them room to condense. Now let's talk about humidity or absolute humidity. Humidity, which may refer to any one of a number of ways of specifying the amount of water vapor in the air. Suppose that when we enclose a volume of air in an imaginary thin elastic container or a parcel about the size of a large balloon, for example, as illustrated, of course, in the next slide, with a chemical drying agent, we can extract the water vapor from the air, weigh it, and contains its mass. If we can compare the vapor's mass with the volume of air in the parcel, we will have determined the absolute humidity of the air. That is, the mass of water vapor is given volume of air, which can be expressed as absolute humidity equals mass of water vapor over volume of air. Or absolute humidity is equals to mass of water vapor divided by volume of air. Absolute humidity represents water vapor density. That means with mass and volume. And normally is expressed as grams of water vapor in a cubic meter of air. For example, if the water vapor is 1 cubic of air weighs 25 grams, the absolute humidity of the air is 25 grams over cubic meter, or 25 grams over m cube. When the same amount of water or same amount of water vapor in a parcel of air, an increase in volume decreases absolute humidity. As what you observe here, an increase of water vapor volume, 10 grams, there is a decrease in the absolute humidity. Once, okay, mass. We have 2 kilograms here of mass, wherein it decrease the absolute humidity. Once we decrease, on the other hand, the mass of the parcel, the absolute humidity increases about 10 grams per cubic meter. So here is the specific humidity does not change as air rises and descends if they have the same mass. Humidity, however, can be expressed in ways that are not influenced by changes in air volume. When the mass of the water vapor in the air parcel is compared with the mass of all the air in the parcel, including, of course, the vapor, the result is called specific humidity. Thus, specific humidity is equals to the mass of water vapor divided by the total mass of air. Another convenient way to express humidity is to compare the mass of the water vapor in the parcel to the mass of the remaining dry air. Humidity expressed in this manner is called the mixing ratio. So the mixing ratio thus gives us mass of water vapor divided by mass of a dry air. Both the specific humidity and mixing ratio are expressed as grams of water vapor per kilogram of air. The specific humidity and mixing ratio of an air parcel remain constant as long as water vapor is not added to or removed from the parcel. So happens because here, this happens because the total number of molecules, and because of that, the mass of the parcel remains constant even as the parcel expands or contracts, since the changes in parcel size do not affect specific humidity and mixing ratio. These two concepts are used extensively in the study of the atmosphere. Now, here the graph, the average specific humidity for each latitude, the highest average values are observed in the tropics and the lowest value in polar regions. Notice in this figure how specific humidity varies with latitude. The average specific humidity is highest in the warm, muggy tropics. As we move away from the tropics, okay, it decreases, reaching its lowest range value in the polar latitudes, both north and south latitudes. Although the major deserts of the world are located near latitudes 30 degrees, this figure shows that at this latitude, the average air contains nearly twice the water vapor as does the air at latitude of 90 degrees north. Because of that, the air of a desert is certainly not dry, nor is the water vapor content extremely low. Since the hot desert air of the Sahara often contains more water vapor than the cold polar air rather north, can we can say that summertime Sahara air has a higher specific humidity. Now, vapor pressure. The air moisture content may also be described by measuring the pressure exerted by the water vapor in the air. Suppose that the air parcel is near the sea level. The total pressure inside the parcel is due to the collisions of all the molecules against the side of the parcel. That means it bombards the side of the container. In other words, the total pressure inside the parcel or of the container is equal to the sum of the pressure of the individual gases. So this phenomenon is known as Dalton's law of partial pressure. It is evident then that because the number of water vapor molecules in any volume of air is small compared to the total number of air molecules in the volume, the actual vapor pressure is normally a small fraction of a total air pressure. Everything else being equal, are more air molecules or the more air molecules in a parcel, the greater the total air pressure. For example, when you blow up a balloon, you increase its pressure by putting in more air. That's why gisa, malupok ang aton nga balloon kung masubrahan ang sudlan sang air. Because the air that you blow inside in the balloon will exert pressure on the surface, putting in more air. Similarly, an increase in the number of water vapor molecules will increase the total vapor pressure. Because of that, the actual vapor pressure is a fairly good measure of the total amount of water vapor in the air. High actual vapor pressure indicates large numbers of water vapor molecules, whereas low actual vapor pressure indicates comparatively small number of vapor molecules. Actual vapor pressure indicates the air total water vapor content, whereas saturation vapor pressure describes how much water vapor is necessary to make the air saturated at any given temperature. Now, in this illustration, the saturation vapor pressure increases with increasing temperature, right? Here, again, the saturation vapor pressure increases with increasing temperature. At a temperature of 10 degrees Celsius, the saturation vapor pressure is about 12 MB, whereas 30 degrees Celsius, the pressure or the vapor pressure is 42 MB here in the 30. The inset here illustrates that the saturation vapor pressure over water is greater than the saturation vapor pressure over the ice. Here. We have several options for describing the amount of moisture in the air. Number one, we have absolute humidity. It tells us the mass of water vapor in a fixed volume of air, or the water vapor density. When we say specific humidity, on the other hand, it measures the mass of water vapor in a fixed total mass of air. And the mixing ratio describes the mass of water vapor in a mixed mass of remaining dry air. And lastly, the actual vapor pressure of air expresses the amount of water vapor in terms of the amount of pressure that the water vapor molecules exerted. We also have an option for describing how much moisture could be added to the atmosphere, and that is through saturation vapor pressure. Saturation vapor pressure is the pressure that the water vapor molecules would exert if the air were saturated with a vapor at a given temperature. Now, while relative humidity is the most common way of describing atmospheric pressure or moisture, it is also, unfortunately, the most misunderstood. The concept of relative humidity may at first seem confusing because it does not indicate the actual amount of water vapor in the air, but instead, it tells us how close the air is to be or is being saturated. The relative humidity or the RH is the ratio of the amount of water vapor actually in the air to the maximum amount of water vapor required for saturation in that particular temperature and pressure. It is the ratio of the air's water vapor content to its capacity. Thus, we write RH is equals to water vapor over water vapor capacity. We can think of actual vapor pressure as a measure of air's actual water vapor content, and the saturation vapor pressure as a measure of air's total capacity for water vapor. Thus, the relative humidity can express as RH equals actual vapor pressure over saturation vapor pressure times 100%. Relative humidity is given as a percent. Okay? Air with a 50% relative humidity actually contains one half the amount of water vapor required for saturation. Air with a 100% relative humidity is said to be saturated because it is filled to capacity with water vapor. Air with a relative humidity greater than 100% is said to be supersaturated, a condition that does not tend to occur often or last longer. Since relative humidity is used so much in the everyday world, let's examine it more closely. So again, a change in relative humidity can be brought about in two primary ways: by changing the air water vapor content and by changing the air temperature. Now, to understand further the relative humidity in this figure, particularly here, figure A, we can see that the increase in water vapor content of the air with no change in air temperature, which is in 20 degrees Celsius, it increases the air's relative humidity. The reason for this increase resides in the fact that as more water vapor molecules are added to the air, there is a greater likelihood that some of the vapor molecules will stick together and condense. Condensation takes place in saturated air, remember? So, as more and more water vapor molecules are added to the air gradually approaches saturation. And the relative humidity of the air will increase because it is already saturated. Conversely, removing water vapor from air decreases the likelihood of saturation when remove the water vapor, which lowers the air's relative humidity. In summary, with no change in air temperature, adding water vapor to the air increases the relative humidity. And removing the water vapor from the air lowers the relative humidity. Again, to emphasize, with no change in air temperature, okay? With no change in air temperature, when we add water vapor to the air, will increase the relative humidity. But when we remove water vapor from the air, it will lower the relative humidity. Always remember that. In figure B here, where's the other? Here. It illustrates that as the air temperature increases from 20 to 30 degrees Celsius with no change in water vapor content, okay, no change in water vapor content, the relative humidity decreases. This decrease in relative humidity occurs because in warmer air, the water vapor molecules are zipping about at such high speeds they are unlikely to join together or condense. Because of faster movement, they cannot condense. The higher the temperature, the faster the molecule speed, right? So the faster the molecule will move, then the less likely saturation will occur. The lower the relative humidity. As the air temperature lower, that means going back to 20 degrees Celsius, the water vapor molecules move more slowly. Condensation then becomes more likely as the air approaches saturation, and the relative humidity will tend to increase. In summary, of course, I want you again to understand and to remember, with no change in water vapor content, an increase in air temperature, that means increase in air temperature, lowers the relative humidity, while a decrease in air temperature raises the relative humidity. Again, I would like to emphasize this. With no change in air temperature, here, with no change in air temperature, when we add water vapor to the air, will increase the relative humidity. When we remove water vapor from the air, will lower the relative humidity. Also, in this portion here, with no change in water vapor content, an increase of temperature, of air temperature, will lower the relative humidity, while a decrease in air temperature raises the relative humidity. Hope that you understand. Now, in application, in many places, the air's total vapor content varies only slightly during the entire day. And so, it is the changing air temperature that primarily regulates the daily variation in relative humidity. Again, changing air temperature that primarily regulates the daily variation of relative humidity. As the air cools, okay, as the air cools during the night, the relative humidity increase. Okay? The relative humidity increases. Remember that always. Because going back to our previous slide, when we increase the temperature, the lower the relative humidity. While we decrease the air temperature, it raises relative humidity. That is why as air cools during the night, the relative humidity increases. Normally, the highest relative humidity occurs in early morning during the coolest part of the day. And as the air warms during the day, the relative humidity decreases. Again, the air as the air warms during the day, the relative humidity decreases. Why? Because going back on our previous slide, if we if we increase in air temperature, it will lower the relative humidity. Okay? That is why as the air warms during the day, the relative humidity will tend to decrease. with the lowest values usually occurring during the warmest part of the afternoon. These changes in relative humidity are important in determining the amount of evaporation from vegetation and wet surfaces. If you water your lawn, for example, on a hot afternoon, when the relative humidity is low, much of the water will evaporate quickly from the lawn instead of soaking into the ground. Watering the same lawn in the evening or during the early morning when the relative humidity is higher will cut down the evaporation and increase the effectiveness of watering. That is why during our elementary days, we are taught by our teachers in EPP that we need to water our plants during the afternoon or during morning, not in the high daylight or high daytime. Because this lesson will tend to explain the scientific background of that lesson taught by our elementary teachers. Because again, when the air cools during the afternoon or during the morning, early morning, the relative humidity increases. Okay? Thus, rate of evaporation is low. That makes our um, watering activity to our plants is much effective than we water our plants during daytime or during a high uh, temperature, particularly during noon or during noontime up to 3 to 4 in the afternoon. Hopefully that you understand the concept of relative humidity in application to our day-to-day living. Now, let's go forward. Relative humidity and dew point. Suppose it is early morning and the outside air is saturated. Okay? The air temperature is 10 degrees Celsius and the relative humidity is 100%. We know from the previous section or previous slides that relative humidity can be expressed as RHO equals to actual vapor pressure divided by saturation vapor pressure times 100%. So as we look back on our previous slides, we can see that the air with a temperature of 10 degrees Celsius has a saturation vapor of 12 MB. Since the air is saturated and relative humidity is 100%, the actual vapor pressure must be the same as the saturation vapor pressure, which is 12 MB. Since relative humidity is 12 MB over 12 MB, sorry, with a 12 MB vapor pressure times 100%. Suppose during the day, the air warms to 30 degrees Celsius with no change in water vapor content or air pressure. Because there is no change in water vapor content, the actual vapor pressure must be the same. Okay? And it was in the early morning when the air was saturated. The saturation vapor pressure, however, has increased because the air temperature has increased. Note that the air with a temperature of 30 degrees Celsius has a saturation vapor of 42 MB. The relative humidity of this Of this, unsaturated warmer air is now much lower as the RH is equals to 12 MB, or the a- actual vapor pressure over the 42 saturation vapor pressure times 100. It is equals to 29%. To what temperature must the outside air with a temperature of 30 degrees Celsius be cooled so that it is once again saturated? So the answer, of course, is 10 degrees Celsius. For this amount of water pressure or water vapor in the air about 10 degrees Celsius is called the dew point pressure, or simply we call it dew point. It represents the temperature to which air would have to be cooled with no change in air pressure or moisture content for saturation to occur. So the dew point is determined with respect to a flat surface of water. When the dew point is determined with respect to a flat surface of ice, it is called frost point. Now, less evaporation means less cooling. And so, we usually feel warmer than we did with a similar air temperature. But a lower relative humidity, when the weather is hot and muggy, a number of heat-related problems can occur. For example, in hot weather, when the human body temperature rises, our hypothalamus gland, or simply hypothalamus, a gland in our brain that regulates body temperature, that sets the thermostat in our body, activates the body heat regulating mechanism. And more than 10 million sweat glands wet the body with as much as 2 liters of liquid per hour. As this perspiration evaporates, rapid loss of water and salt can result in a chemical imbalance that may lead to painful heat cramps. And that is for the effect of relative humidity in with regards to human discomfort. Now, we have here heat stroke. Excessive water loss through perspiring coupled with an increasing body temperature can result a heat exhaustion. It will result fatigue, headache, nausea, and even fainting. In If one's body temperature rises above about 41 degrees Celsius, heat stroke can occur, resulting in complete failure of the circulatory functions. If the body temperature continues to rise, death may result. In fact, each year across the North America, hundreds of people die from heat-related maladies. Even strong, healthy individuals can succumb to heat stroke, as did in the Minnesota Vikings All-Pro offensive lineman Corey Stinger, who collapsed after practice in Mankato, Minnesota on July 31, 2001, and died 15 hours later. Before Stringer fainted, the temperatures on the practice field were about 90 degrees Fahrenheit, with the relative humidity of 55%. So, in an effort to draw attention to this serious weather related health hazard, an index called the heat index, okay, is used by the National Weather Service. The index combines air temperature with relative humidity to determine an apparent temperature, what the temperature feels like to the average person for various combinations of air temperature and relative humidity. Now, in measuring humidity, humidity is most often measured through automated instruments, though some measurements are still taken manually at some observing sites. One common instrument used to obtain dew point and relative humidity is the psychrometer, which consists of two liquid in glass thermometers mounted side by side and attached to a piece of metal that has either a handle or chain at one end. The thermometers are exactly alike with our psychrometer, except that one has a piece of cloth or we known as a wick covering the bulb. The wick covered thermometer called the wet bulb. Okay, this one, the wet bulb. The wet bulb is dipped in a clean, usually distilled water, while the other thermometer is kept dry. This one. Both thermometers are ventilated for a few minutes, either by being whirled or sling psychrometer, or by having air drawn past it with an electric fan, or known as the aspirated psychrometer. Water evaporates from the wick, this portion, and the thermometer cools. The drier the air, the greater the amount of evaporation and cooling. After a few minutes, the wick covered thermometer will cool to the lowest value possible. Recall, we can recall from an earlier section that this is the wet bulb temperature, the lowest temperature that can be attained by evaporating water into the air. The dry thermometer here, commonly called as dry bulb, gives the current air temperature or the dry bulb temperature. The temperature difference between the dry bulb and the wet bulb is known as the wet bulb depression. A large depression indicates that a great deal of water can evaporate into the air and the relative humidity is low. The small depression indicates that little evaporation of water vapor is possible. So the air is close to saturation and the relative humidity is high. If there is no depression, the dry bulb and the wet bulb and dew point are the same. And the air is saturated and the relative humidity is 100%. Also, we have here the hygrometer. The instrument that measures the humidity are called hygrometers. One type called the hair hygrometer. Hair hygrometer is constructed on the principle that the length of the human hair increases by 2.5% as the relative humidity increases from 0 to 100%. This instrument uses human or hair or horse hair or a synthetic fiber to measure relative humidity. A number of strands of hair with oils removed are attached to a system of levers here in this portion. Because the hair hygrometer is not as accurate as the psychrometer, especially at very high and very low relative humidities and very low temperatures, it requires frequent calibration, principally in areas that experience large daily variations in relative humidity. Also, we have the automated instrument that measures humidity is the electrical hygrometer. Automated instrument that measures humidity is the electrical hygrometer. It consists of a flat plate coated with a film carbon an electric current is sent across the plate. As water vapor is absorbed, the electrical resistance of the carbon coating will change. These changes are translated into relative humidity. This instrument is commonly used in the radiosode, which gathers atmospheric data at various levels above the Earth. Still another instrument, the infrared hygrometer. Another is infrared hygrometer that measures atmospheric humidity by measuring the amount of infrared energy absorbed by water vapor in a sample of air. And the dew cell determines the amount of water vapor in the air by measuring the air's actual water vapor pressure. The dew point hygrometer measures the dew point temperature by cooling the surface of a mirror until observation forms. This sensor is the type that measures a dew point temperature in the hundreds of fully automated weather stations. Or what do we mean again? The ASOS, or the Automated Surface Observing System, that exists throughout the United States. I guess this will be the last slide. And here are the online references for you to look into it. Okay? Thank you for your kind attention. Hopefully that you've learned something from this video lecture and can be applicable in your day-to-day living. Thank you very much and have a nice day.